Hi, everyone. We will give another minute here or so for people to jump in, and then we will begin. Thanks to everyone for joining, and stay tuned. We'll get started here very soon, just in another minute. Thanks. All right, it's the top of the hour. Let's go ahead and get started. Good afternoon and evening, everyone. Welcome to AFL's From Glitches to Glory, OTDR Problem Solving Strategies webinar. I'm Charlie Collius, the Global Product Marketing Manager for the Equipment Group here at AFL. We're delighted to have you all here today for part two, or the second of our two webinars on OTDRs. And if you'd like to see a replay of the first episode titled Fiber Optics Demystified, OTDR Fundamentals, it can be found on learn.aflglobal.com, and then click in the top menu to browse by product, and then click Test and Inspection, and you will see it listed. Again, that link is learn.aflglobal.com for a replay of part one of our OTDR webinar series. Before we begin today, I just want to go over some housekeeping tips. All attendees here are in listen-only mode to reduce background noise during this webinar. The slide deck is available to download under the Handouts tab in your control panel on your screen. Throughout today's presentation, please feel free to submit any questions you have using the questions box in the control panel on your screen. We will answer these at the end of the presentation, so don't hesitate to ask during the session. Today's webinar is being recorded, should last about 50 minutes, and a link with where to view the recording will be sent out tomorrow along with a certificate of completion. So right now, it's my pleasure to introduce Michael Scholten, who is our presenter today. Michael is a Senior Product Line Manager for OTDRs here at AFL. He has over 20 years of experience in fiber optic network test, including product marketing, systems engineering, product management, hardware, and software development. Michael, you may begin anytime you're ready.
Great, thanks a lot, Charlie. And welcome, good morning, good afternoon, good evening, wherever you are. And again, welcome to part two of our presentation. In this one, we'll talk about common OTDR test setup errors, and these include the distance range being too long or too short, ghosts and echoes, pulse width or averaging time too long or too short, misconfigured launch or tail cords, an incorrect index of refraction, incorrect pass-fail limits, incorrect event detection thresholds, and then multi-pulse versus single pulse expert mode, or multi-pulse, what we call smart auto versus single pulse expert mode. We'll also talk about common network issues. Some of this is a repeat from the part one presentation, but reinforcement is always good. So poor launch quality, dirty or damaged or mismatched connectors, poor splices and macro bends, and misinterpreted events. And then we'll close with some common reporting errors for those folks who must generate a report once they've completed their OTDR testing. And these could be failing to save your results, incorrectly naming them, a desire to add or correct events or delete false events in your report. So common OTDR setup errors. We'll start with distance range being too long or too short. This would only occur in expert mode or real-time mode. In smart auto mode, the test set itself will determine the length of the fiber under test or the network under test, and will pick an appropriate distance. But if you deem yourself to be an expert user and you go in and you then have control of the range setting, how far the OTDR tests. If your range is too long, then you'll see a compressed trace at the start with, in this case, 2/3 of your trace just showing noise, and it's not useful information. If your range is too short, in this case, you'll see that the fiber continues beyond the end of the trace itself. So we see fiber in a reflective event here at the start, but there's no drop to the noise floor at the end, and you can't get an accurate measure of the length of the fiber under test. Corrective actions: make sure that your distance range setting is at least 20% longer than the tested network. If you are using launch or tail cords, make sure you include the length of those when estimating the expected fiber length. So if you had a 2-kilometer network, but you're using a 150-meter launch cord plus a 150-meter tail cord, you need to be 20% longer than that 2.3 kilometers that with the extra launch and tail cord, the total length grows a little bit. If your range is too long, reduce the test distance range setting. If your range is too short, simply increase it. If you're not sure what your fiber length is, you could use real-time mode with a long range setting. Visually look for the end where you see the drop to noise, and then go back into your expert mode to do time-based averaging with a more appropriate distance setting. Echo events. These occur due to re-reflections in the network under test when you have some very high reflections in the network. Those high reflections can occur at dirty or damaged connectors where you have an air gap, or due to an open UPC at the end of the network. In this case here, I've shown a very poor connection at cursor A, followed by an open end or another poor connection at cursor B. And then beyond cursor B, you'll see reflective spikes. These are echo events due to re-reflections, where either you have the second reflection at cursor B being re-reflected off the reflection at cursor A and generating a secondary echo at twice the distance from A to B, or I'd say the same distance from A to B, that much later than B. If you have re-reflections off your internal optics, then you'll get these smaller reflections here that are the same distance from the start to the beginning of the acquisition. And in FlexScans, we have a 50-meter internal launch cable represented by this shaded pink region, and that's we're getting a re-reflection off our internal optics here. So here again, we have 150 meters between strong reflections, resulting in 150 meters to this echo reflection. Corrective action: you can ignore echoes beyond the end of the fiber if you're looking at an expert mode trace. Event analysis will, in this case, you see that these echo reflections are not identified as events. So the software itself has been able to determine that these are echo events, not real events, and it has not classified them as events. You can also identify echoes based on the spacing after large reflections if you're visually looking at it, as I've done here. Ghost events. So sometimes people are confused about the difference between an echo event and a ghost event. An echo event is a re-reflection. A ghost event occurs when you've selected a test range that is shorter than the network under test, and there are some large reflections in the rest of the network beyond the range that you've selected. In this case, those large reflections get aliased back into the start, and you'll see them appear as spikes in your trace at a location where there are no events. The corrective action for this is to make sure that Either you're using a smart auto mode, in which case the OTDR will automatically select a range that's longer than the network under test. Or if you're using expert mode, make sure that you've picked a range that is longer than the network under test. If you change the range setting and you see these ghost events move or disappear, then you'll know that they were indeed ghost events. Another common setup error in expert mode tests is picking a pulse width that is either too long or too short. If your pulse is too short, then the backscatter will descend into the noise before the end. And you see that the 1310 trace here, the red trace, has gotten very noisy well before the fiber end. The 1550 nanometer trace is also becoming noisy before the fiber end. And again, this is because of pulse width that's too narrow. If the pulse width is too long, then closely spaced events can overlap. So in this case, we've used, looks like about a 200 nanosecond pulse width, which is 20 meters long. We have two events here that are overlapping, and they've been detected as a single event rather than as two separate events. You may often have, if you use a jumper, short jumper to connect your OTDR to the network under test, it may be only 2 or 3 meters long, and you would need a very narrow pulse width to be able to separate those as two events. That's why we always recommend using a longer launch cable to separate the OTDR connection from the connection to the network under test, so you can truly qualify independently qualify the connection to the network under test. So again, corrective actions here. Use automatic settings, preferably a multi-pulse setting. I'll talk more about that in a minute. If multi-pulse test is not available, you may need to perform multiple tests in expert mode, one that uses short pulse widths to detect these closely spaced events during the beginning of the network under test, and then a separate test with a longer pulse width to be able to obtain sufficient dynamic range to test to the end of longer networks, or to test through the high loss of splitters in passive optical networks. So in expert mode, select a longer pulse if you're not able to reach the end of the fiber with the current pulse width. Select shorter pulse width to prevent these closely spaced events from overlapping. Another setup error is your averaging time is too short. Averaging is used to pull the backscatter level up out of the noise, or to, in essence, suppress the noise. The longer you average, the more you can suppress the noise. If you see your trace descending into the noise before the end of the fiber, that's an indication that you may not have enough averaging time. And in this case, your trace could be too noisy to detect some events of interest. You know, as you reach the end of this 1310 nanometer trace and the noise becomes more and more apparent, you would not be able to detect small non-reflective events, including a poor splice. One interesting item is that the black 1550 nanometer trace has less slope to it than the 1310 nanometer trace does. And that's because the loss per distance at 1550 nanometer is always less than at 1310 nanometer, and is a reason that 1550 nanometer is used to in long haul networks and in WDM wavelength division multiplex networks. Corrective actions here increase the averaging time to reduce noise, but keep in mind that the law of diminishing returns applies. Each doubling of the averaging time will reduce noise by about 0.75 dB. So that means if you tested for 1 second, you would get a certain signal to noise ratio. If you doubled that to 2 seconds, you would reduce noise by 0.75 dB, but then you have to double to 4 seconds, then to 8 seconds, then to 16 seconds, 32 seconds for half a minute, then a minute, and then 2 minutes, and So it takes longer and longer to get that next 0.75 dB improvement in signal to noise ratio. And pretty soon you just don't want to run a test that's long. Wider pulse widths will also effectively reduce noise, but you could end up with the overlapping events due to the longer dead zone from the reflections, as we discussed in the previous slide. A misconfigured launch cable. So as I mentioned, you always want to connect to your network under test using a launch cable to separate the OTDR connection from the first connection to the network under test. When you do so, you may have misconfigured the launch cable. So in this case, I'm showing that 150-foot launch cable was configured when in fact 150-meter launch cable was used. And a meter is a little bit more than 3 times or a little bit more than 3 feet long. So you'll see that 150-meter launch cable, the reflection at the end of the launch cable, which is the actual start of the network, is well beyond the 150-foot configured launch cable, which is this shaded blue region. As a result, the start of the network is reported at the end of that 150-meter or 150-foot launch cable, and we see a second event being reported at the actual end of the launch cable. And our third event being reported out here at about 2350 feet is quite a bit longer than the actual length would be from the end of the launch cable to this event here. If the reverse of that could happen where you configured a launch cable too long. In this case, we configured a 1,000-meter launch cable, but only a 20-meter launch cable was used. The OTDR interprets the start of the event at the end of, or the start of the network at the end of that 1,000-meter launch cable. So that's distance 0. And the reported length to the end is the distance from event 1 at 0 distance and event 2, when in fact the actual length would have been from the end of that 20-meter launch cable out to the end. So incorrect launch cable configuration will result in incorrect length measurements and may hide some events that are within the misconfigured launch cable, or may report an extra event because your configured launch cable didn't include the full length of the actual launch cable. Corrective actions, you can use the OTDR to measure the launch cable length itself before connecting to the network under test. So just leave the end of your launch cable open, run an OTDR test, see what the length to the end is reported, and then use that to configure it. AFL launch cables are labeled with the length on them, so you can enter that length. And there's some tolerance in the actual length, but the OTDR will automatically adjust within a few percent for a launch cable actual length that's within a few percent of the configured length. You can correct misconfigured launch cables in the reporting software. AFL Flex reports will allow you to do that, so that if you did misconfigure when you ran the test, you don't have to go back out to the field and repeat the test. If you failed to use a launch cable or your launch cable was too short, in this case, you won't necessarily be able to separate the connector, the connection to the network under test, from the OTDR connection, or the OTDR connection will be your connection to the network under test. And you may not be able to get an accurate measure of the loss of your connection to the network under test. So in this case, we show no launch cable being used and a pulse width too wide to measure the launch of the first connection, even though we have a 50-meter launch cable inside the OTDR. we see that the backscatter level inside the OTDR hasn't reached the full level before we see the reflection from the connection to the network under test. And that means we will not be able to accurately measure the loss of event 1 here, the connection to the network under test. Corrective actions, make sure you use a launch cable which is longer than the pulse widths you expect to use. In smart auto mode or multi-pulse acquisition mode, we'll use narrow pulse widths to measure the connections at the beginning. But in expert mode, you're in control of your pulse width setting, and you do want to make sure that you use a launch cable that's longer than the pulse width. Now, launch cables are measured in meters, but your pulse widths are measured in nanoseconds. How do you make the association? We'll use the rule of thumb that it's 10 nanoseconds per meter. So a 200 nanosecond pulse width is 20 times 10 nanoseconds. That means a 200 nanosecond pulse width would be 20 meters long. And if you have events within that first 20 meters, then you want a launch cable that's longer than 20 meters to be able to measure that first connection. As I said, multi-pulse OTDRs always use short pulse widths at the start of the fiber, so a shorter launch cable is okay. AFL recommends the use of 150 meter launch cable for networks that are even up to 50 kilometers long. Incorrect group index of refraction. If you remember from our first presentation, the way an OTDR works is it injects pulses of light into the network under test. They travel down the fiber, backscatter and reflections travel back up the fiber, and the OTDR measures the round trip of light to reflections and backscatter at various points in the network. How does the OTDR convert that round trip time of flight into distance? Well, we know the speed of light in glass, in fiber, and that's based on the index of refraction. Different fiber types have slightly different indices of refraction, and the index of refraction may also be abbreviated as GIR for group index or IOR for index of refraction. If your index of refraction is set incorrectly, at the beginning of your trace, you'll see that events are correctly aligned, but at the end of the trace, you may see that they are misaligned. And that's an indication that one or both of the indices of refraction for your 1310 and your 1550 wavelengths is not set correctly. In the FlexScan OTDRs, you can select the fiber type. The most typical fiber type is G.652 fiber. If you're testing a PON network within a subscriber's premise, they may be using G.657 bend insensitive fiber. Those two fibers have different indices of refraction, and so you want to select the right fiber type. If it's a long haul network, they may have used dispersion optimized fiber for 1550 nanometer, and again, it has a different index of refraction. Corrective actions use the default setting for the known fiber types, and I've identified some of those common fiber types here. Review and correct your IOR settings if you do see that your end is misaligned, and if the misalignment is enough, this will show as two separate events, even though we know the fiber only has one end. If you reduce the IOR, it will lengthen the distance reported for that wavelength. And you'll see in the table that the index of refraction, it does depend on the wavelength. So slightly different value for 1310 nanometer than for 1550 nanometer. If you're testing live PON using 1625 or 1650 nanometer, the IOR will be slightly different yet again. A wrong pass-fail limit. So often you have your OTDR evaluate the whether a splice or a connector passes or fails. Usually it's evaluated in the US against TIA 568.3 limits. Internationally, it may be evaluated against ITU-T G.651 or IEC pass-fail limits. There's commonality across these standards. So typical splice loss number for both of these standards, or all three of the standards, is 0.3 dB. Connector loss may be 0.5 dB or 0.75 dB. And reflectance of your connector is connector dependent. Your splices are non-reflective, so there is no reflectance spec for them. Your connectors will have a reflectance spec depending on the type of connector. So typical polished convex or PC connectors has minus 35 dB reflectance pass-fail limit. And ultra polished convex has a better or lower connector reflectance limit of minus 45 dB. And angle polished connectors have an even better, meaning even lower reflectance limit of minus 55 dB. Oftentimes, customers will set their own pass-fail limits. Fusion splicers, such as Fujikura splicers, have become so good these days that customers often, or users often, want their splice loss to be much better than the 0.3 dB, and a more typical number may be as tight as 0.1 dB. So you want to make sure that if you're a contractor doing installation for a service provider, that you understand what their pass-fail limits are and you set up your OTDR to apply those pass-fail limits. Some extra notes here: OTDRs cannot actually detect the connector type. They can determine whether an event is a connector or a splice, but they can't, when it is a connector, the OTDR can't automatically determine if it's PC, UPC, or APC. And in some cases, the MPO or multi-fiber connectors may have more relaxed limits because it's harder to keep all 12 fibers in an MPO connector aligned as precisely as a single fiber connector can. Also note that the loss at the end of the open end of a network under test cannot be evaluated. And that's because we're going from backscatter level before the open end to no backscatter level after it. So there's not measurable loss in that case. Once again, if you applied the wrong pass-fail limits when you ran your test, your offline reporting software may be able to correct and reapply modified pass-fail limits. Wrong event detection thresholds. So it's possible that visually obvious events are not detected, even with a low noise trace. In this case, the detection threshold is set too high. Another possible case is that many false events are reported, especially as the noise level increases towards the end of the trace. In this case, your detection threshold is set too low. Corrective actions with older OTDRs adjust the event detection thresholds to find the small events without producing too many false events. Alternatively, use a newer OTDR such as our FlexScan OTDRs, which automatically adjust the event detection thresholds based on the backscatter signal to noise ratio. So close in, where we have a very clean trace, a good signal to noise ratio, the event analysis software will use much tighter limits and will be able to detect smaller non-reflective loss events. As the noise increases further down the trace, the automatic event analysis software will relax its detection thresholds. It won't be able to detect this as small events, but it also won't produce false events. Multi-pulse smart auto versus single pulse with expert mode. Some years ago, multi-pulse OTDRs were introduced, and it really has provided a big benefit to users. Single pulse with OTDR, when you run a test, you have to select the pulse width you're using, and as we discussed earlier, too narrow a pulse width and you may not be able to see to the end of the trace. Too wide a pulse width and closely spaced events may overlap. So if you're limited to an expert mode that supports only one pulse width per test, then you may need to run multiple tests in order to detect the closely spaced events at the start, but still be able to test reliably to the end of those longer networks or through high loss splitters. In this case, use an OTDR that supports multi-pulse acquisition. With multi-pulse acquisition, the OTDR combines a mix of short and wide pulse widths in a single test, and that allows it to detect closely spaced events at the start of the network without sacrificing the dynamic range needed to test longer fibers all the way to the end. So in this case, you see that we have a 50-kilometer network, yet we're still able to detect events that are only 20 meters apart at the start of the network. So common network issues, what are the problems that could occur in your network? How do they manifest themselves, and how do you detect them? So key factors affecting optical network performance could be the received power level due to optical loss through the network, reflections in the network, and chromatic dispersion or polarization mode dispersion, primarily on much higher speed networks, 10 gigabit per second and above. So how do low power excess loss, reflection, and dispersion impact performance? Well, your optical system performance degrades and your bit error rate increases, or you'll begin to experience packet loss and packet retransmission in packet-based networks, meaning that your overall communication throughput will go down. When the received power is too low due to too much optical loss, then your communication through that network can fail entirely. So what to do when system performance degrades or fails? First thing you can do is check your system power levels. Verify the output power level of a transmitter. If it's absent or too low, you're going to have to replace the optical transmitter, the laser in that network. Check your receive power level. If your transmit power level was okay, but you're not getting enough power at the far end of the network before it goes into your receiver, if it's absent or too low, check for excess loss in your optical network. If your receive power is okay, but you're experiencing degraded performance, check for excess reflections in the optical network. And then lastly, if there was no excess reflections in your operating very high speed network, check for chromatic dispersion and polarization mode dispersion. What are the primary causes of optical networks? This is a little refresher from our first presentation. It's poor connections and poor splices. Contamination on the connector end face, poor polishing of the ferrule, the end face of the ferrule, damage to the optical connector due to repeated matings without cleaning, or damage on the ferrule end face. Poor splicing, possibly because you didn't maintain your cleaver or you didn't keep your splicer V grooves clean. And then lastly, excess bending, macro bends. You fail to take appropriate care of the bending when you finished your splice and dress the excess fiber inside your splice case or inside your cabinet. So causes, dirty, damaged, or mismatched connectors. Make sure you're always clean your connectors before mating. And never mate blue PC or UPC connectors to angled APC connectors, which usually have a green body on them. The flat end face of that PC connector mated to the angled end face of the APC connector will create an air gap, and you will get a 4% reflection off that blue UPC end face. Make sure your connectors are fully seated in their bulkhead adapters, and make sure you replace damaged connectors with, preferably today, with factory polished connectors rather than doing field polishing. And factory polished connectors are available in both splice on, fusion splice on, or a mechanical splice. The Fujikura Fuse Connect and the Fast Connect are examples of fusion spliced on or mechanically spliced on. Pour splices. Make sure you strip, clean, and cleave in that order. Make sure you maintain your fusion splicer and rotate the cleaver blade when it's worn. And be aware that core alignment machines produce better splices than cladding alignment. And that's especially true if you're not doing a very good job of stripping and cleaning the buffer coating off of your fiber. And then be aware of fiber breaks. So backhoe fade, when some contractor has unfortunately dug up your cable and broken some fibers there. Rodents, they love to chew on those fibers, and they may damage them in the process. And then maintenance activity. Someone's gone in to maybe add a new user or reconfigure a fiber network and unintentionally disconnected an in-service network. Dirty, damaged, or mismatched connectors. How will these show up? They will show up as excess reflections in your network under test. Excess reflection will have a clipped or saturated top, and there will be a long recovery tail as you come down from that spike. And you may see re-reflection echoes in your trace. Your corrective actions here, inspect and clean the OTDR and launch cable connections. And let me reinforce that. Make sure you inspect and clean both the OTDR connections and your launch cable connections. And if you encounter some of these multiple reflections in your network under test, it's likely due to dirty or damaged connectors, so go out there and inspect and clean them as well. If cleaning doesn't remove the contamination, it's likely that your end face is pitted from mating one or two dirty connectors, and cleaning isn't going to fix that problem. So now you need to replace those connectors with field installable fusion splice or mechanically spliced on connectors. Make sure you have no mismatched connectors. If you have blue to green, you're going to have to replace one of those, either make them both blue or both green. And as shown in the illustration here, UPC to UPC will give you a good connection, assuming they're both clean and undamaged. APC to APC will give you a better connection, and that's because if you do have even a slight air gap in there, the angle on the end face will generate a reflection that is at a sharp enough angle that it's not captured and guided back up the fiber. So you won't get re-reflections resulting from poor APC to APC connections. Poor splices and macro bends in your network. If you have excess loss at a splice, how do you determine whether it's a poor splice or different fiber types or macro bend? And if you compare the results at multiple wavelengths, this is how you can determine whether they're poor splices or whether they're macro bends. And if you see a gainer followed by a loss, And in this case, our event 8 is a gainer event, and event 9 looks like an excess loss. That's due to a fiber mismatch. Here at event 6, we see that we have essentially no loss at 1310 nanometer, a half dB of loss at 1550 nanometer, and 1.5 dB loss at 1650 nanometer. The loss through a bend is wavelength dependent. And the longer the wavelength, the more loss you will have due to bending. And so by comparing the trace at 1310, a shorter wavelength, to the trace at 1550, when we see a higher loss at 1550 than at 1310, that's a good indication that there's a macro bend in the network. And if it's even higher still at 1625 or 1650, you can be pretty certain that you have a macro bend at that location. How do you resolve poor splices and macro bends? Well, if your loss is similar at all three wavelengths as we see at event 4, resplice and retest. In the case of event 9, we do have similar loss at all three wavelengths. Resplicing and retesting isn't going to fix this, and that's because the excess loss here is due to a difference in the fiber characteristics, and the gainer preceding that excess loss is an indication that we have a fiber mismatch. Bidirectional testing and averaging is one way to correct for the excess loss and the gain and see the true loss of when you have a fiber mismatch. In the case of macro bends, once you've determined that you have a macro bend, then you have to go into your typically splice closure or cabinet and look for the tight bend in your fiber. And then eliminate that tight bend, redress the fiber in that cabinet. If it's not obvious to you where that is, you may be able to inject a visual fault locator or visual fiber identifier, basically a red laser, into a nearby end of that fiber and look for the glow coming out at the macro bend location. If you have breaks inside the fiber itself, you also get a red glow at that point. And the FlexScan OTDRs include a built-in visual fault locator to help with isolating these types of faults. This interpreted event. So a good APC connector may be displayed as a passing or failing splice. The OTDR interprets non-reflective events as splices. If your good APC, a clean undamaged APC, produces a non-reflective event, the OTDR will likely interpret it as a splice. But the connector loss across that APC is typically more than 0.3 of a dB. And so the OTDR may interpret it as a failing splice. With event correction built into the OTDR, you can go in and change the event type from splice to connector. The OTDR will automatically reapply connector pass-fail limits. And if the loss of that event is less than the connector pass-fail limit that you've configured, then it will that failing splice will become a passing connector. Pass-fail limits are similar for mechanical splice and a connector. So in that case, you typically don't need to make any correction. Network too long to test at 1310. I mentioned earlier that the loss per distance is higher at 1310 than it is at 1550. It's also higher at 1310 than it is at 1625 or 1650 nanometer. So if you typical out of service test is done at 1310 and 1550 nanometer, but if you test a long haul DWDM network at 1310 nanometer, your trace may fall into the noise before you get to the end. And that those networks are simply too long to be operated and tested at 1310 nanometer. You could test it at 1550 only, but then you wouldn't be able to detect macro bends because you have to compare the loss at a shorter wavelength to the loss at a longer wavelength in order to detect macro bends. So if you have an OTDR that includes 1310, 1550, and 1625 or 1650, you could choose to test that network at 1550 and 1625. And here you see that the trace at 50 kilometers is beginning to get pretty noisy at 1310, but it's less noisy at 1550 and 1625. And again, by testing at 1550 and 1625, now you have a test at a short wavelength and a long wavelength. If you did have a macro bend in it, you would be able to determine that by the difference in the loss at that event at 1550 and 1625. So I'll start to wrap up here with common reporting issues. Did you forget to save your results? If that's a likely problem for you, enable autosave so that every time a test completes, the OTDR will automatically save the results into a folder that is under your control, and auto increment the fiber number so that your next test doesn't overwrite, but sequentially numbers your results. Know your naming requirements so that you don't name your results incorrectly. In FlexScan OTDRs, you can name a project or a job. You can name the near end and the far end location names. You can provide a different name for the cable itself, and a starting fiber number. And then, as I said, every time you save a results, that fiber number will automatically increment. And your offline reporting software may be able to correct your naming, so you don't have to go out and repeat the tests if you save them incorrectly. But it's going to be a whole lot easier for you to name them correctly to begin with. If you have misconfigured launch or receive cable settings, you may be able to correct those in your offline reporting software. And if you have missed events, you may be able to add them. If you have misinterpreted events, you may be able to correct them. If you have false events, you may be able to delete them. And all of these capabilities are supported by AFL's Flex Reports software. And I'll wrap up with a word from our sponsor, which is AFL. There's an industry challenge today, and that's to improve test productivity and efficiency. The industry is experiencing a shortage of skilled fiber technicians ever since the COVID pandemic. At the same time, we have competing service providers racing to deploy fiber to the home and 5G fiber backhaul to provide ever more bandwidth, broadband bandwidth to subscribers like you and me. So that means a new crop of technicians must be productive. They must be able to perform first-time right diagnosis and repair. So to do that, you want OTDRs which are easy to configure, meaning they have simple, intuitive controls. Seldom used features are either buried or hidden to prevent misconfiguration or confusion, but still available to expert users. And you have large controls which don't require a stylus to operate. The results should be easy to understand. So most OTDRs today provide an icon-based link map and an event table. The color-coded link map indicates the pass-fail status, and the symbols in each of the icons identify the icon as a connector, a splice, a splitter, or a macro band. And the OTDR should recommend corrective actions for failing events. Reduce your test time. An instant on OTDR means you don't have to wait before you can begin your testing. And smart auto multi-pulse acquisition means that you don't have to run multiple expert mode tests to detect your closely spaced events at the near end while you using separate tests with wider pulse widths to test far down the fiber. An all-in-one OTDR with an optical light source, an optical power meter, and a VFL allows you to measure output power, to generate fiber identifying tones, to perform your fault locating using your OTDR, and making your length, loss, and ORL measurements. And when you've identified macro bends, but they're not jumping out at you, you can use your red laser to try to pinpoint them. Small, handheld, even pocket-sized, rugged, and weather-resistant, makes it well-suited for the outside plant. And then it should be available with fast, comprehensive reporting software. AFL's test and inspection product lines cover 5 areas. So OTDRs and optical troubleshooters, which has really been the focus of this presentation. Our inspection and cleaning products, including Focus Flex for single fibers, Focus Lightning 2 for multi-fiber connectors such as MPO and the new MMC connectors, coupled with one-click cleaners, wipes, cleaning fluid. Optical loss testing, we have handheld light sources and power meters, as well as our Flow Scout pond power meter. And on the fiber identification side, we have clamp-on non-intrusive optical fiber identifiers, as well as very small handheld visual fiber identifier, red laser, standalone red laser. And all of these product lines are kind of brought together in our reporting software. So your OTDR results can be put together with your inspection results and your power meter and loss results. And with that, I'll wrap up. And if we have some time for questions, I'd be happy to entertain them.
Great, thank you very much, Michael. And we did receive a large number of questions. We have about 9 minutes left, so I'm going to launch into these to maximize our time here. The first one, can you repeat this? This was asked towards the end of the presentation here. Can you repeat the recommendation regarding launch fiber cables? So earlier in the presentation, you recommended 1,000 meters, and towards the end, you were speaking of 150 to 200 meters, possibly relating to pulse width. So if you could just clarify that a little bit.
Sure. So I showed an application in which a 1,000-meter launch cable was configured, but the launch cable itself, the actual launch cable, was only 20 meters long. If you're using Smart Auto, then there are very few applications in which you would need a 1,000-meter launch cable. The only time I would expect you might want a longer launch cable such as that would be if you're testing a pond network and you're connecting directly to the splitter itself. So you have a very high loss event right at the start. You want to see good backscatter level before you go through that splitter, and you need to have enough feeder fiber beyond that splitter for the backscatter level to be detected there to measure the loss through that splitter. In most applications, when you're using Smart Auto mode, I would recommend 150 meter, and that's because we're using Smart Auto mode will use narrower pulse widths at the start, and the launch cable is right there at the start. If you want to qualify the loss of the connector at the end of the network, then you must use a tail cord. You can't just leave that connector open. And since a wider pulse width is going to be used at the end of the network, far down the network, at the far end of the network, you will need potentially a longer receive cord or tail cord to connect to that far end. It really depends on the length of the network. If you're up to 10 kilometers long, then 150 meter tail cord is going to be fine, assuming that you don't have any excess loss or high loss splitters in that first 10 kilometers. If you're testing a 50 kilometer network, you're probably going to need a 500 meter, 1,000 meter tail cord if you want to measure the loss of that far end connector. Now, service providers will rarely use a tail cord, and that's because one advantage of the OTDR is it's a single-ended test. If you need to connect a tail cord, then it becomes a two-person, two-ended test. You need someone at that far end to connect that tail cord. Next question.
Great. Next one, does any AFL OTDR have a helix factor variable that we can input before testing?
Today, we do not include a helix factor variable. You can use the IOR to really compensate for the helix factor. And for those who don't understand what helix factor is, the OTDR measures the length of the fiber, which is always longer than the length of the cable. And that's because in a multi-fiber cable, the fibers are spiral wound as they go through the cable. And that means that the total length of the fiber is longer than the cable itself. The helix factor can be used to correct for that. So if you know your fiber is 1% longer than your cable, you can put in a helix factor that will correct for that. You could similarly adjust your IOR by 1% to accomplish the same thing.
What types of fiber splices are recommended for the lowest loss?
Most certainly fusion splices, and when you do fusion splicing, you have a choice between a core alignment machine, which uses cameras and images the core of the fiber itself through which the light travels. That will give you the best alignment. If you use a cladding alignment machine, it's aligning the fibers based on the outside cladding, the typical 125 micron cladding on a single mode fiber. And if the core is not perfectly centered, you can have your cladding being perfectly aligned, but your cores are offset a little, and so you'll get a little bit higher loss. Fusion splicing will almost always produce, I'd say will always produce lower loss, and if you do good cleaving, no reflectance, whereas a mechanical splice in which you've stripped, cleaned, and cleaved your fibers, even if you have perfect 90-degree cleaves on the end, the mechanical splices rely on index matching gel to prevent excess reflections at the glass air interface, because you won't get perfect contact between those. And that index matching gel will typically produce a reflectance of around minus 55 dB. And your mechanical alignment, if it's good, you'll get losses that are more like connector losses than like fusion splice losses.
Okay. Somebody asked, what is the difference between a micro bend and a macro bend that you referenced?
Yeah, so macro bends are caused by external activity once you've installed the cable. And if you apply too tight a bend to that cable, you can introduce a macro bend. And depending on the fiber you're using, there's a recommended minimum bend radius. Micro bends are typically caused by exerting excess force on the fiber, either due to poor cable installation practices when you're pulling the cable, and the cable sheathing is not decoupled from the fiber itself, or your pulling termination is not properly installed. Or if you get water into a cable and it freezes, it will apply external pressure on those fibers, and that pressure will result in micro bends. The micro bends tend to be distributed over a longer distance, whereas a macro bend will tend to be isolated at a single location where that external bend has been introduced.
Great. A comment from one of the viewers that said backhoe fade. Backhoe fade is a lot less common than auger fade these days, and that augers can rip the cables out of the splice cases too. I just wanted to throw that out for everybody here. And then a question from someone else, OTDR launch level value shows dB instead of dBm. Why is that? And does launch level differ between pulse widths?
Yeah, so we don't. When we're making OTDR measurements, we really only care about the relative difference events in fiber. And so independent of what the output power level is. Can you hear me now?
Yes, Ken. Yes, absolutely.
Sorry, Charlie, I'm not sure if I'm hearing you or not.
You seem to be dropping out, Mike.
Yeah, okay.
Yeah, maybe well, go ahead, Michael, if you can hear me. If not, we'll just wrap it up because we're right at the top of the hour here.
Yeah, okay. So now I forgot.
That's okay. You know what? You're fading out. So what I'm going to do, Mike, is I'm just going to end it here. And thank you for your presentation, and thanks everyone for your questions and attending today. So if we did not get to your question, and we had quite a few of them, so if we didn't get to them, we will get back to you with an answer. As we did in part one, we put together a digest, and I don't see why we won't do the same thing here and send that out for everyone. So a survey will pop up here as we end, and we appreciate all of your comments on this and future webinars. And a link will also be sent tomorrow to the recording of today's webinar, where to view part one, and a certificate of completion. And we look forward to seeing everyone at our next equipment group webinar sometime this summer. So everyone have a good day and a good evening. Thank you very much.
Thank you, Charlie.